And I'd just like to extend a warm welcome to everyone who's come out. It's kind of flattering that this many people will come out on a Wednesday night to listen. So tonight I was asked to talk about what if plastic was not used in facial scrubs. And that seems a bit of a flippant question. I did a radio interview earlier and they were sort of wondering why we would do a whole talk on plastic in facial scrubs. But as you'll see, this is just one example and we're going to continue through and talk about some of the other problems with plastic use. Okay, so we're going to talk about plastics, a little bit about what plastics are. If anyone is a polymer chemist, try not to listen while I mangle it a little bit. We're going to talk about plastic waste entering the marine environments, why that is a problem. We're going to talk a little bit about the big floating bits, and we're going to talk a lot more about microplastics, the smaller particles. And hopefully we're going to finish off talking about some solutions. Now the picture in the background is taken in the Canary Islands in Tenerife. It's a holiday area off the coast of Africa. And as you can see, there's quite a lot of sort of floating coloured bits in there, and that's all plastic. Something possibly we don't quite see that level of plastic here, but it was quite startling to me to see how many small bits of plastic were present. So just to start off with, what are plastics? Now these are polymers, so if you can think of polymers a bit like a fibre, these are things that when we heat them, they will soften and we can mould them. And that's one of the reasons that we really like plastic, is because we can mould it, we can make it into shapes that we want. Now, what we do with the polymers, they're long chains. Basically, if you can think of, they're like you have sort of subunits that when we heat them, they join together and we get these long repeating chains. What kind of plastics are we talking about? Most of us will be familiar and most of us will be wearing some form of plastic tonight. These are the main classes, there's 7 of them. So PET at the bottom, that's your soft drink bottle. PVC, that's sort of sidings of buildings and the kind of material that you would use in drain pipes. It's a little bit less popular at the moment because of some toxicity issues with it. Polystyrene, the meat trays and fruit trays at the supermarket. Polyurethane you see in coatings, and polyethylene and polypropylene are very highly used plastics. We use a lot in the laboratories, so nice clean plastics. They're high density plastics, so they're nice and strong. What do we use them for? I almost thought maybe I should title this, what don't we use them for? We really love plastic. So widely used packaging materials, building materials, medicinal uses. And one use that people might not be so familiar with are as abrasives. We use them quite a lot, and that's how come they're actually used in facial scrubs. But if you see pictures of people's houses, and there's some fantastic images taken by National Geographic where they get people to take everything out of their house and it gets photographed. And as you move into more developed countries, it's quite startling that when people have everything out of their house being photographed, how much of it is plastic, how much we rely on it. Why do we use it so much? One of the things, it's lightweight. We like that. It's very light materials, so that produces uses that we wouldn't necessarily think of. It's very durable. This is a permanent material. You can use it for a very long time. It's easily molded, so we can make it into shapes. We can make it into bottles. We can make it into vacuum cleaners. We can make it into pipes. We can make it into tubes. Often used because it's chemically resistant. That's one of the reasons that I use it in the laboratory. I can put very corrosive or highly acidic solutions in there and they're going to stay in the bottle. I don't have to worry about them escaping. A big use, of course, is plastic packaging. We like it for waterproofing. Reduces energy use in transport. If you're moving around large amounts of soft drinks, then if it's in a plastic bottle versus a glass bottle, you'll use less energy. There's also some evidence that using plastic reduces food waste, because we can keep the air out, we can keep the moisture out, we can keep the bugs out by using plastic. How much are we producing? It's quite startling. Plastics only really came into being after World War II, and there were 1.9 tonnes produced in 1950. In 2013, there were 330 million tonnes, and increasing. And if you look at that graph there, the one at the bottom, the blue is European plastic production and the orange is world plastic production. It pretty much looks exponential to me. It doesn't look like it's stopping anytime soon. So there's large amounts of plastic are being produced. What are they made from? Well, they're made from coal, oil and gas, so they're made from fossil fuels. Now we are increasingly use plant-based feedstocks, so soy and corn are becoming more common. But one thing I need to stress there is just because it's made from a plant doesn't make it any less durable. When they make the plastics from plant-based materials, they are identical to the materials that they are making from fossil fuels. So they will have the same problems, the same properties of lasting for a very long time. Now, plastics are basically made from carbon. Back to my not so great description at the beginning, where we have groups of atoms. So these groups of atoms are called a monomer. So if you imagine we've got like a small building block, and they are the smallest repeating unit in that plastic. We then join a whole lot of those building blocks together, and that's how we make the big pieces of plastic. So like this. So this is polyvinyl chloride. Here we have the small unit, so this is the monomer. We then undergo a chemical reaction and we form these long chains. So that's the basis of forming all plastics. So quite a lot of energy has to actually go into this process, and it's surprising how much energy is used to produce plastic. By the time you refine the chemicals that you need from oil or gas or from plant material, and then you form the plastics, then you've already produced a large amount of energy. It's about 6 times what it would take to produce glass to make an equivalent amount of plastic. The other thing we need to think about is plastics often contain other chemicals. They might contain fillers. They do contain colouring agents. So Dyson vacuum cleaners, possibly shouldn't say a brand name, they're yellow. The reason they're yellow is because they've got cadmium in them. You may have other heavy metals to give the red or the blue or the green colours. They may also have stabilisers, so things that make the plastics more resistant to heat, or we add UV filters, which is the same as when we put sunblock on ourselves, that stops the plastics from being degraded. So that would be particularly important if you were using a plastic material in an awning or an outside for a building, that you would want it to be UV stable for as long as possible. We also add a lot of flame retardants. So this room will be full of flame retardants in the plastics. That stops them burning. So the computers, the telephone, probably these as well. A lot of plastics have flame retardants. And as you'll see later, some of these additives can be problematic. One of the first additives that people started sort of controlling were plasticizers. So it's kids' soft squishy toys and soft squishy balls. Those kind of materials initially had a lot of what are called plasticizers, and they give that nice soft squishy texture. Now they've been controlled for about 20 years in Europe when they realised that these high levels of plasticizers, so some of the phthalates, were not good for human health, and were particularly not good if you had like a teething toy or something that children would put in their mouths. So what do we know about what happens to used plastics? Now this is variable. You get differences happening between developed and undeveloped countries, and different countries will have different programs. But around the world, about 10% of the solid waste stream is plastic. This either ends up in landfills, so hole in the ground, which will itself usually be lined with plastic to stop things leaching out. Incineration, now that can be problematic for some of the plastics, particularly if they contain additives. That incineration may be toxic. There is very limited recycling, and they tend to be released into the wider environment. There's some quite tragic things. Some areas of Africa, they joke about the plastic bags being the national flower because there's so many of them in the trees. What happens in New Zealand? Well, again, we're similar, about 8% by landfill. We throw away 200,000 tonnes of plastic each year. This one surprised me, 22 million shopping bags each week. So this is figures from an environmental recycling facility in Hamilton, and also from the Ministry for the Environment. We only recycle about 20% of the plastic, and of the 7 types, we only recycle 3. So there's quite a lot of plastic that we don't do anything with. Why are we worried about them? They're natural, made of carbon, they'll be fine. No. They generally are degraded very slowly, if at all. So we're talking decades, if not longer. This fact really kind of bothered me. Most plastic produced still exists somewhere on Earth. Some of it will have been destroyed during incineration, but most of it is still somewhere. This is material we only started producing post-World War II. We've still got it. They are lightweight and strong materials. So because they're lightweight, they will be transported by wind. They will transport on the tides. And because they're strong and they're not breaking down, if they get caught on things, then an animal can't release itself from it. We have a very large volume of plastics being produced, as I showed in the earlier slides, and that's increasing. And of course, we use a very large amount of energy to make plastics, much of which we only use once or maybe twice. So about 5 to 12 million tonnes of plastics go into the world's oceans each year. About 80% of that plastic is derived from land. Some of it will be from lost fishing fleet materials, nets and things, but most of it's from land. It's been estimated that up to about 150 million tonnes have already been discharged into the oceans. And the prediction is that there's going to be about 1 kilo of plastic in the oceans for every 3 kilos of fish, which is kind of something that made me sit and think for quite a while. Still makes me think. Once plastic gets out in the environment, we can classify it into two ways. So the macroplastics. These are the big chunks. These are the visible ones. They are often mistaken for food by wildlife, and we've all seen the tragic pictures where organisms have completely filled their gut. This picture of this bird here, it's a young bird. It's likely been fed those plastic objects by its parents. One of the other things that is worrying is there's been this big increase in entanglement in the last 10 years, and that's where animals get stuck. Plastic gets wrapped around them, it gets stuck. And you see horrendous pictures for all sorts of marine mammals, marine birds, fish, range of things. One thing that's important too with some of these items is there will be species differences in what they will pick up. So a bird in Australia, when it wants to impress the girls, it collects things and takes it back to its nest. It preferentially likes blue things, so blue plastic is a problem. But there are other species that might preferentially like green or yellow objects because they look like something it would normally eat. So you will see differences in species in what they pick up. This is quite an interesting story about how far plastics can go around the world. It's kind of cute but also kind of terrifying. So in 1992, a boat leaving China lost a cargo of bathtub ducks. Now they can trace where they've gone because of the type they were and what they had written on them. About 10,000 of them drifted north, so about 10,000 went this way, and about 20,000 came our direction. It took 15 years from them to go from here round through and ending up on the beaches in Britain. This is actually from the Daily Mail, who did this lovely chart. But I think this just shows you how far things can go once they get into the oceans. These are light, they're a floating material, they're very durable, and when they're being packed up, there are also some frogs, apparently, so they're still recognisable 10 to 15 years later as rubber ducks and frogs. So, despite the fact they've spent 15 years in the ocean moving. And you wonder how many of them got eaten. Some of you will have heard about the ocean gyres, or the Great Pacific Garbage Patch. So this is a highly stylized image. It's lovely. It's showing broken bits of plastic. And there are 5 of them. And this is where the currents kind of swirl up and wash up some of the plastics. The plastics, of course, are not really this visible. They're not big bits of plastic. It's more sort of mushed up like a soup of plastic materials. And these are the microplastics. So once the big bits of plastic get broken down, then they form these really fine plastics. If we can get the plastics out while they're still big, then we've got a chance of dealing with the amount of plastic that's going into the oceans. Once they become the microplastics that I'm going to talk about next, it is actually not feasible to remove them. It just wouldn't economically, or just not feasible. I'm not even sure how you would go about removing plastic in that form. So microplastics, now there's a bit of still people, this is relatively new in the literature, people are still debating over the ideal definition. NOAA, which is the, one of the American oceanography institutes, their definition is less than 5 millimetres. Some people will use less than 1 millimetre, some people will use less than 10 millimetres. But we're talking small plastic. Some of it will be visible to the naked eye, some of it won't. Now it comes in two types. We've got primary microplastics. So these are plastic pellets, like this image here. A lot of plastic is transported around the world in this form. It's easy. These are called nurdles. This is the material that would come into New Zealand or to other countries where plastics are made. So you can melt this down, you can mould it, you can form whatever application that you would want. And some of the big problems have come from this kind of material being dropped off ships. What's also problematic is what we call the secondary microplastics, and these are formed from breakdown of larger plastic materials. So as these larger plastic materials go into the oceans, they break down and form these small fragments. Some of the sources, as I said, for primary microplastics are if we're going to make plastic goods. Another source, which I think is a completely sort of flippant and sort of daft use of small amounts of plastic, is the microbeads that are in facial cleaners and toothpaste. These are not easily removed by wastewater treatment plants, so once we put these beads into our wastewater systems, they will go through a wastewater treatment plant and will be discharged out the other end. We also have a range of synthetic abrasives that might be used in industrial purposes as well, of these preformed plastic beads. They're very hard, so they work very well, but also they're very light, so you can transport them. This image at the bottom is actually from a paper that was done at the University of Auckland, where I quite like the title, Contributing to Marine Pollution by Washing Your Face, Microplastics and Facial Cleansers. And this was some of the first work in New Zealand where they actually went through and looked at what's in facial cleansers and identified that microplastics were here. Now, the companies are very upfront. If you look at the products, they tell you they contain microbeads, they tell you they contain plastics. And one of my students who was working on microplastics suddenly twigged and brought in all of her face creams and things, and we had a look through, and quite a lot of them did contain microplastics. So these products are available in New Zealand. The secondary microplastics are formed once the big chunks get out into the environment, then they're either broken down by sunlight. The sunlight weakens the plastic and it will start breaking into smaller parts. You also have the action of wind and wave, so you can get friction as plastic washes up and down the beaches. So just if you think of how glass sometimes gets polished on the beach, the plastics will tend to break. When they've been exposed to a lot of sunlight, they will become more brittle as well. Another, what we would probably put in the secondary microplastics is fibres released from clothing during washing. So synthetic clothes can release a very large amount of fibres into the environment. We had a bit of fun in the lab. One of my students who's sitting up the back, who did some work on microplastics and was looking using microscopy to identify and was trialling some methods, was kind of grumpy and kind of amused when he brought me some images and you could actually see the fibres off the red top I'd been wearing. That sort of gave you an idea of how much fibre we all shed and what might come off our clothes. And there was a very distinctive red, and it was there in the photographs. I didn't wear that top again in the lab until the work was finished. What happens when these microplastics get out into the environment will depend on what kind of plastic they're made from. A lot of plastics will float. Some of the heavier ones will sink. So if they sink, they will end up in the sediments. The ones that float can be moved around, and they can move long distances, so they can go out with the tides, they can be blown with wind. Once they're in the water body, they can be colonised by organisms, and I'm going to talk a little bit more about that. Now that, when they get colonised, might make them heavier, so they might sink. They can be consumed, and I'll talk about the effects of that, and they can end up in the sediments. So we've got some that will end up in the sediments and some that will move with the waves. Now I should say that some of the, recently some of the deep dives that they've done looking in the sediments, deep ocean trenches and things, they have found microplastics. Plastics are everywhere. How do we get them if we're going to do some analysis? Well, first of all, if it's sediment, you can sieve it. So depending on what size you're looking for, you can put it through a sieve, so just like a garden sieve. You can also use density-based separation techniques. So basically you make a solution that is very dense, so we normally use this with salt. We went through bags of sodium chloride. There are other methods as well. And you make the plastics float on top. So what you're trying to do is separate out the sort of sand particles and your plastics on top. You can also do it with organisms as well, or biota. How you do that is you dissolve the organism in acid. The plastics will not dissolve in acid, so hopefully if you can dissolve away the rest of the organism, you've still got the plastic. For seawater, generally it's filtering large volumes of water, and they also tow nets. So they may take nets over several kilometres or sort of big transects to try and pack up. Now, of course, this is all limited by what sizes you can target, what size your filters and your meshes are. It's very time-consuming work to get the microplastics out. Once we've got the microplastics, we still need to be able to identify them. Is that a piece of shell? Is that a microplastic? And there will be other co-extracted materials. I don't yet know of an analytical chemistry technique that will only get out what you're looking for. You normally have to get rid of some other junk. So some of the work is through microscopes, identifying, and that's very long and very tedious, manually looking down the microscopes and identifying the plastics. We can also use spectroscopy or light-based measurement techniques. So we look at how our plastic fragments interact with light. And from that we can work out whether that's a plastic or that's a piece of shell or something we may not even be sure what it is. And what we can do is we can take, and I'm going to show you that, reference materials. So we can take plastic that we know the composition, look at the pattern of the light that we get, and we can compare what we get in our samples to that light. So microplastics have basically been found everywhere. And that's the fibres, the plastic fragments, and also the particularly the plastic pellets or the nurdles that are used for manufacture. So widespread in ocean waters and beach sediments and in remote areas, places where we've never expected to see material. They've been found in lakes, they've been found frozen into the Arctic sea ice. And they have been found in a very large number of marine animals, particularly in shellfish, plankton, fish, seabirds, and some of our sort of iconic species like dolphins. This here is from a piece of work that was done over about 5 years. This was a multinational effort. What they did was they looked to see it was 5 years worth of data. They used towing of nets over areas to try and work out the microplastics and then modelled the distribution. What you can see here is we've got 4 different sizes from 0.33 to 1 millimetre, from 1 millimetre to nearly 5, from nearly 5 to 200 millimetres. What you can see is the hot spots. This is where they predict the highest concentrations of plastic will be. Now that's partly due to ocean currents, and of course in some of these areas it's due to sheer population size. This sort of translates to where the most people are. But of course, because these materials are very light, we can't just assume that concentrations will be highest where populations are, because they can move as well. So what do we know for Canterbury? This is Phil collecting samples. You'll note he's wearing all cotton clothing. Looked at 10 beach sites in 2013. He found, because he did all the work with the sieving and the floating, found them at 8 out of 10 locations. We looked at a range of urban areas. This is all beaches. And the concentrations were around 45 microplastics per kg of sediment. And this was kind of consistent with what is being found elsewhere in the world for people using similar techniques. I found some data yesterday, which was from off the coast of China. They were finding 200 to 400 particles per 50 grams of sediment, which is probably to do with that increased population size where you have more plastic. The majority of the plastics were white or clear. Now this is of concern because these are the colours that some organisms will target because they look like a food species. It's just showing you, I talked about identification. So here, this is basically looking at in red, these are the fingerprints, in black are the fingerprints of the particles interacting with light. This is by Raman spectroscopy. So these are our reference samples. So we had a bit of fun identifying enough reference samples. And in red is actually the particles. So you can see we're able to work out what kind of plastics they were. These are all very light plastics which will float. So we've got all this plastic. Does it really matter if the beaches turn to plastic? You know, it's an inert material. Do we have to worry about it? Well, I think we do. One of the problems are when these microplastics are ingested by aquatic organisms is that they will often deliberately do it. The size of the plastics are similar to food items, so plankton and fish eggs, so an organism actually thinks it's getting a meal. There are some organisms that are particularly susceptible to taking up microplastics, and these may be things like polychaete worms that live in the sediment, and their feeding strategy is to chew their way through the sediment. So they're going to actually ingest it as they go through. They're not very selective about what they're doing, they're just chewing. Or you may have things like shellfish, like mussels, which are filter feeders. So their feeding strategy is to sort of open up and filter out the particles. And most of the particles that they would have traditionally come across or previously come across would have had some nutritional value. That's how they were feeding. They were taking out plankton, they were taking out small amounts of organic material. What the problem with that is we've now got these animals that have now got they're full. Plastics don't necessarily pass through and they don't break down. So what happens is these organisms are now think they've had a meal, but they haven't. So they can starve because they're not hungry, so it doesn't trigger them to feed, but they're not getting any nutritional value. Now, there have been problems with movement, growth, and reproduction, and there's some evidence to suggest that we can get transfer from a predator species to a prey species of the plastics. So people are starting to wonder, well, does it matter if we're exposed to them? And I have to be honest, the science has got as far as saying, well, we are finding microplastics in seafood. And there's been a big study recently come out of Belgium where they found significant amounts of microplastics in mussels. But we haven't really figured out yet what that means and how much of a problem that might be for us. One of the other problems with these plastics when they get ingested by organisms is that they can be a vector for contaminants. What this means is that there are some contaminants, because of their properties, will stick to the plastic. Or they may be in the plastic because they may be one of the additives that are added to the plastic. So then when the animal ingests that plastic, then the processes in the gastrointestinal tract may then release those contaminants so they can be taken up by the organism. The other problem is if we get contaminants stuck onto the plastic, they can transfer very long distances. They're protected from degradation. So microorganisms are less likely to degrade them, and they're not likely to be broken down by sunlight if they're stuck to a plastic particle. They're protected. So they may move distances that we wouldn't expect. So this has become a problem for some of our sort of legacy contaminants, some of the POPs, the persistent organic pollutants, is it's been found that they can accumulate from water. They're not very soluble in water, so we wouldn't necessarily expect there to be a lot in marine environments, but they can stick onto the plastic and then travel wherever the plastic goes. And as I said, you can have those additives being leached out as well. Or something like Bisphenol A, which is used in making polycarbonate plastics. There's some concerns around the toxicity of that. So if an organism ingests small fragments of polycarbonate plastic, then the bisphenol A can leach out into the organism. Now this works really well, this kind of absorption and carrying around on contaminants. This is a program run out of Japan called Pallet Watch, and this is quite neat. What they're doing is they're getting people to send in plastic that they find on beaches all around the world, and from that they're getting an idea of global distribution of contaminants. So these are some of our legacies. So this is DDT, which is a pesticide. There are others, some of the flame retardants. There are some of the polycyclic aromatic hydrocarbons, which are significant environmental contaminants that we produce anytime we burn anything. And they're quite toxic. So this is an example where someone's actually using that ability of the plastics to pick up contaminants to get an idea of what global distributions might look like. We worry about the plastic monomers and additives because it's shown that they can accumulate in organisms, and some of them are endocrine disrupting chemicals, which means that they will impact on the messenger systems of organisms. So it may make them so some of them can be estrogenic, so they may give a false signal of more estrogen being present. Some of them can work on the thyroid system. Now that's important for some of our species because the thyroid system is what helps organisms regulate body temperature and keep warm. So we may not want them to be receiving these contaminants. One of the other problems is we don't really understand what effects of mixtures will do. And so we've got organisms being exposed to quite a range of contaminants. Some of them will be on the plastics, some of them will be on the food. I should also say that metals also transport on some of the plastics as well. Some people, and this is a little bit outside my area because I'm a chemist, not a biologist, I'm quite firm on that, chemist, not biologist, but microplastics can also become colonised by marine organisms. So marine organisms can live on them. Now, this can also happen with the macroplastics as well. And because the plastics get transported long distances, if you've got an invasive species that's on there, that might be a way for it to move from one area to another, where it might not be able to do that in the open waterway without the protection of being on a plastic. These images here, just want to show the kind of fouling. We're all used to seeing organisms growing on plastics. This one here is a plastic bead, and this is from near the New Zealand coastline, and it has barnacles on it. Now, so that can then move distances as well. So what can we do about this? What are some of the solutions? Well, a classic kind of environmental approach is that reuse, reduce, recycle. And I think that's going to become important for working with plastics as well. There's a lot of voluntary action around the world. There are around community-driven initiatives to reduce plastic use. You're probably all not aware, but this is Plastic-Free July. You might have thought it was Dry July. It's Plastic-Free July. This is an initiative that came out of Perth where they are encouraging people to give up single-use plastics, to not use straws, to not use drink bottles, to not use the caps you get on the coffee that stops you spilling it on yourself. So they're encouraging people to look at reducing the amount of plastic. And this has gone, I think there's now people who've signed up from about 80 countries around the world. There's of course always regulatory action. And there are some jurisdictions overseas where they've targeted plastic bag usage. And you may either have to pay to use them or you can't use them. There's been some initiatives in New Zealand over the weekend around increasing recycling of plastic bags and plastic packaging. There's going to be a trial run funded by the government. There are moves against having the plastic beads in the cosmetics. Now, I think the plastic beads probably initially went into facial scrubs because people were concerned about using, traditionally it was things like apricot kernel or oat husk, and people were probably worried about allergies as well. But there are moves, so Illinois in the US has banned the use of microbeads in cosmetics, and New South Wales is asking the Australian federal government for an Australian-wide ban. And as I said, we do have limits for plasticizer concentrations. We have limits for the kind of chemicals that might be present in plastics in children's toys, and that's been around for a while. We can enhance recycling. And I would argue that we need to think of end-of-life plastic as a resource. Quite a lot of effort and energy has gone into producing that plastic, and then it just gets thrown away. This would reduce the use of fossil fuels. It reduces the need for waste management. If we can take 10% of our waste stream out, then that's a significant reduction in the amount of waste that's being produced. The problem is going to be is that plastic materials will need to be designed to be recycled. We may need to think about what plastics we can use. How many different plastics can you have in an item? Can we use red plastics? What kind of additives can we use in plastics so that we can actually recycle them and use them as a resource? We do have biodegradable plastics, but these aren't really the answer. They generally don't degrade fast enough and the kind of time frame that we would need to avoid environmental damage. The other problem is they tend to disintegrate into small pieces, which doesn't really solve the microplastics issue. We've now just designed something that will make small bits that can be released into the environment. They may not degrade at all under the conditions in landfills, so basically we're just storing that plastic for later. If it's going to break down into small pieces, then it can be released out into groundwater or surface water and ultimately make its way to the ocean. And the other problem that people argue against using biodegradable plastics, it doesn't actually encourage people to change their behaviour or to reduce plastics. So I think we need to reevaluate what is an appropriate use of plastic. These are permanent materials. Should we be using them for single or short-term uses? Are there uses that we think are perfectly fine for short-term, or there might be single uses, say medical applications, we say that's fine. Plastic toys with takeaway meals, maybe that's not a good use. That's one of my pet peeves. Maybe plastic straws are not a good use. Maybe we can actually start thinking about when do we use plastic and when do we not. Now, this is something that has gone on with any kind of consumer product and any kind of chemical that we use, as we're constantly reevaluating what can we use, what can't we use, when should we be using them, and when shouldn't we be using them. Okay. So to finish off in summary, we have large volumes of plastics entering the world's oceans. That doesn't look like it's going to abate anytime soon on the amount of plastic that's being produced. And as I said, once that plastic forms microplastics, we are not going to be able to readily remove that. There are some people who are saying that perhaps the amount of plastic that's gone into the oceans is going to be more significant for the oceans, at least in the short term, than the effects of climate change, because we already have this large amount of plastic in the oceans. Why we're so worried about the microplastics is because they've been shown to be very widespread. Anywhere basically that people look for them, they generally find them. And because of that ability for them to vector organisms and contaminants. Of course, plastics are permanent materials. These are things for 70 years. And my argument would be that we do as a society need to consider what are appropriate uses of plastics.